Thank you very much. And it's a pleasure to see so many of you here at the end of a very long day, but I think you'll agree it's been a really exciting day with some fantastic talks. I've been really looking forward to this talk, and at this point, normally what happens is a chair will say lots and lots and lots of wonderful things about the incoming keynote speaker. But I spoke to Gillian earlier on, and she said, no, don't do any of that. Just say who I am and then get off the stage. So for once in my life, I'm actually going to do as I'm told, which doesn't really happen very often. So I've been really looking forward to hearing about the first results from the James Webb Space Telescope. And so it's my pleasure to introduce Professor Gillian Wright, who is the director of the UK Astronomy Technology Centre and also the principal investigator of the mid-infrared instrument on the James Webb Space Telescope, and the team that Gillian led out of UK ATC. So Gillian, over to you.
Thank you. Well, thank you for inviting me, Sarah. I'm kind of amazed to be here and giving a keynote talk and having some data to share with you all. So where to start? Well, how about that I start by sort of saying what I'm going to cover. So I'm going to talk a bit about the mission. I am going to talk about the MIRI instrument just because that's the thing I've led and that I know most about, a little bit about what happened during commissioning. And then there's so much science out there that I have to say that this is some selected science and my personal favorite bits and the things that have got big hints in them about what might happen in the future. So where to start? Well, how about this? Biggest Christmas present you could imagine for the astronomy community, and a long-awaited one. So there's been a lot of anticipation about what would happen when JWST started taking data, and it was just fantastic to finally launch, even if it was on Christmas Day. And rather a nice, I think it is a Christmas present for the whole astronomy community. So a quick summary about what JWST is. It is the biggest telescope ever launched into space by a long way. It's a deployable infrared telescope. So the primary mirror is 6.5 meters across. That is bigger than the biggest rocket fairing. So the only way to get it into space is not to build a traditional telescope with a single primary mirror, but to build it in pieces and fold it up. The telescope has to operate at cryogenic temperatures in order to be sensitive and to have instruments optimized in the infrared. And it is now keeping Gaia company at L2, about 1 million miles away from Earth. L2 is really important for JWST, not just because of it's dark, but because that sunshade that you can see in the picture only works if the back of the sunshade is at the sun. So the telescope must always be in a configuration where the sunshade is pointing to the sun. And the launch on Christmas Day was absolutely perfect. The trajectory needed hardly any course corrections at all to get us to L2. And that means we now are expecting a 20-year plus science mission from JWST. So that was the first piece of good news, although we didn't know it at the time. So it is a little bit of history. It is an international project. It is NASA's flagship mission, but it has major partnership from both ESA and the Canadian Space Agency. And I joined the team in 1997 when we were working on early instrument design studies and thinking about what the right instruments would be for a large deployed infrared telescope in space. In the usual way of things, there's a lot of talk in the science community and work done as you're leading up to these things. So it was around 1999 when NASA formally entered into a partnership with ESA and the Canadian Space Agency. And that was when the kind of phase A designs of the mission began in earnest, and it moved beyond scientists talking about, isn't this a good idea? So a little bit more history. The construction began in 2004 of the mirrors because they were a very long lead item because of the need to precision polish them, and each individual mirror is already quite a large mirror for a spacecraft. So each one of those segments is about 1 meter across. In the meantime, there was still some ongoing discussions that some people in this room probably remember only too well, about exactly what the share of who was going to do what to create this new mission would be. So it wasn't until 2005 that it was settled that JWST would launch on an ESA-provided Ariane 5 rocket. And that was also when the final kind of who was going to do what about MIRI was sorted out as part of those arrangements. And the mirrors were completed in 2011. We actually delivered MIRI to NASA in 2012, the hardware. And in between, in that time frame that's not mentioned on this chart, there was a lot of threat to the mission around the mission being cancelled, and I'll come back to that in just a minute. And then the telescope was actually finished in 2016. We've had numerous long ground test campaigns with the telescope to make sure everything is absolutely functioning perfectly. And then the launch was 2021. So there are many years of development and testing, 25 years in fact, and it is one of the most ambitious space projects in the history of astronomy and space science. Those sunshades that provide the cooling, so the whole telescope is passively cooled just by the big pink sunshade that you can see up there. They're huge. They are tennis court sized. They're made of thin, lightweight material, and there has to be 5 layers, all not only stretched taut individually, but accurately spaced and positioned with respect to each other in order for the cooling to work properly. And so there's a number of engineering firsts here. The first one is the passive cooling of such a big structure. Deploying a telescope in space, that's not been done. Segmented mirrors in space has not been done. We had done. The Keck telescope is a segmented mirror telescope of kind of the 8-meter class. So to the extent that in ground-based astronomy, segmented mirrors had been used, but never done in space and under the kind of autonomy that you need to do this kind of thing in space. Phasing of the segments, and also, of course, the whole telescope is at 40 Kelvin. It's not nice, friendly, ground-based observatory in the warm, under the vacuum of space. The MIRI development, the low power and vibration field free cooler for MIRI was also a massive technical development that had not been done before, and without which I wouldn't be here telling you about lots of science. I think the sophistication of the instruments and the spectrometers and the flexibility of them, and something that I've been thinking about more recently is actually the fidelity of the computing that was used to do the engineering modeling and the verification of things by model rather than by test, just because it was so big and complicated, is also a new and paid off in spades, as I hope I'm going to show you. So I mentioned it was an infrared telescope. By looking at infrared wavelengths, we can look at things that you cannot see in the optical. So you're looking at the universe in a new and a different way. It's also because we know that as we look further out into the universe, the light from the galaxies is redshift. So it's reddened just because it's so far away and the galaxies are traveling away from us. So you need an infrared telescope to follow up some of the discoveries and things that we already know about from Hubble and other missions. So that then that's where the concept of an infrared telescope came from. In Europe, in the end, we provided the Ariane 5 launcher. NIRSpec was provided directly by ESA through contracts to industry, and MIRI was a little bit different because MIRI was provided by additional contributions of the member states. So, and ESA are also a part of the operations of the mission at STSCI. So lots and lots of companies and universities and organizations from all over Europe have been part of constructing this mission. And bringing that closer to home, I think there's been a big involvement in the UK. So we have led the MIRI consortium. So we played a really leading role in making MIRI happen in the UK, and some big centres contributing. The UKTC here at RAL Space, I'll talk about that a little bit more. Airbus, the University of Leicester, and then in the science team, Cardiff, Durham, and UCL as well. So we had we really got leadership role for all of MIRI. It's worth noting that as well, ESA appointed scientists to the NERSPEC science team supporting the industry procurement from the University of Cambridge and Oxford. So it hasn't been all just MIRI, but also the capabilities of JWST are really well matched to science that astronomers in the UK want to do. So 40% of the science observations in the first year of JWST operations have a named UK investigator, so somebody in a leadership role. And I think a huge number of people all across the UK are involved now in doing science with JWST. We also won a bigger share than any other country other than the US of that first year of operations telescope time. And the single largest program that was awarded time has a UK PI. So I think, it's a measure of how welcome this is to the community. So there are 4 instruments on JWST, and that provides 17 different ways of observing, because the instruments, as I said, are quite sophisticated and complicated, and they have a number of different observing modes. I wanted to just talk a little bit about MIRI. MIRI actually accounts for quite a lot of those 17 ways of observing, but it is the mid-infrared instrument, and it was in the end provided as a 50-50 partnership between the nationally funded consortium in Europe and the US. And the reasons it became agreed as a partnership was originally when JWST was conceived, the ideas were all around near-infrared science. And so NASA and ESA had already been talking about, a near-infrared camera and a near-infrared spectrograph and the scientific priorities around that. But the community also wanted a mid-infrared instrument. And this was a way, the science community, of making that mid-infrared science happen. It has to be said that in terms of what was needed to build MIRI, it is more technically complicated because it has to be cooled to 7 Kelvin in order for mid-infrared detectors to work. So you are not just putting the optics to measure the light onto your cryogenic, passively cool, deployable, great big complicated observatory. You are also then adding a requirement to have a cooling system to cool one of the instruments even further. So the whole of JWST is cooled to 40 Kelvin, which is minus 233 degrees centigrade. MIRI is operated at 7 Kelvin, so it's another 33 degrees colder, which just adds a whole, it's two pieces, not one. So the 50-50 partnership is how we built and developed MIRI. And one of the reasons we wanted MIRI is sort of summarized in this diagram. It's about how much infrared wavelength capability and more capability that you add to the observatory by moving to the mid-infrared. So you can see the tiny little bit of visible, which is where we look. In the optical and the light, we can see the near infrared. You're picking up things that are galaxies that are redshifted, much cooler red sources, and dust starts to become transparent in the near infrared because it is much less efficient at absorbing optical light. In the mid-infrared, the dust can become even more transparent, or you can look at the dust. So then you're looking at the dust that is being warmed by the stars rather than looking through the dust at the stars. And that is a key thing that you need if you want to study how planets are forming in disks around other stars, because that is all tied up, not just with the physics of the collapse of the star and the planets, but with the chemistry of what's happening with the dust and the ices. So you want to be able to look at as well as into the dust. So there's only one mid-infrared instrument on JWST, so we just packed it full of all the capability we could. So we can take images. Clearly, it's a mid-infrared camera. We can also we also built in coronagraphs. What coronagraphs are used for is they put a tiny little spot that blocks out the light from the star so that you can actually see directly any planets that are near to that star. So this is just like you going out and looking at the sun and putting your hand up like this to kind of shade it. It's the same technique. You're just blocking out the source of the really bright light so that you can see things, next to it. We developed 4 coronagraphs. You can see them stacked down the side of that. 3 of those are a specially developed technology called phase mask coronagraphs. So instead of having an actual spot, they work by moving the phase of the light to cancel the light out exactly in the center. One of the reasons we really wanted to do this was because we wanted our coronagraphs, although we're working at longer wavelengths, we wanted our coronagraphs to be able to work in tandem with the coronagraphs and the near-infrared spectrograph. So scientifically, these were, but we also put in a classical coronagraph. You can see it, it's the thing that's got the dark blue spot. We also built a spectrometer. So at this point, we're now 2 instruments really, because we're NIRCam and NIRSpec, but in the mid-infrared. Our spectrometer is done 2 ways. One is a classical slit spectrometer that splits the light up into its rainbow of components. And the second one is what we call an integral field spectrometer. It takes a spectrum of every point in an image so that afterwards you can reconstruct exactly where the different spectra have come from in your image. And this is the MIRI team that developed MIRI. You can see a number of institutes, and now I'm not going to read out all the things people did, but basically we came from 10 ESA member states. In each country, we had our own national funding. It was a partnership, a collaboration to build the instrument. And then we joined with JPL, won the contract from NASA to provide, the US provided parts of MIRI along with the University of Arizona. And although this way of additional contributions from the member states is not unusual in the ESA program, it's certainly unusual in the NASA program. So we were kind of, everybody was waiting to make sure that all the pieces had fallen into place. We were the last instrument to start, in a formal sense, to start our activities. So I thought it was nice to do a little bit of history. So this is some of building the flight model of MIRI, and I'm going to be very parochial and UK-centric about this. So building the flight model MIRI started at the University of Leicester, who were responsible for leading the primary structure that holds all the optics together. And the black hexapod that you can see there is made of carbon fiber. It's to thermally isolate us from the rest of JWST. If you have to be colder than the thing you're attached to, you better thermally isolate yourself from it thoroughly. So the thermal design was led from RAL Space, and the structural design was led from the University of Leicester. So this is MIRI starting to come together at the University of Leicester, with some very happy people finally putting a flight model together. And this was, I believe, around March 2010, thereabouts. And it was shortly followed down to RAL by the spectrometer pre-optics. So while the UKTC led the consortium, we were also responsible for a lot of the spectrograph design. And this is the part of the spectrograph that has the integral field units that do the spectroscopy, split the light up so you can do spectroscopy of every point of light in a field. Also accompanied by a very smiling team. By then it was all wrapped up in its nicely sealed, keep it clean package and out the clean room, and on its way to RAL a few months after the primary structure. And the integration process kind of took a long time, and then we had a year of testing. But this is the beautiful image of the flight model MIRI under test at RAL. The little bobbly things that you can see are optical references that we were using to check that the alignment of MIRI was all lined up. There's a model of it too, if you want to come and have another look. And after that, and a test campaign and a final delivery review, sequence review with ESA, we packed it up at RAL and sent it off to NASA. So this was in May 2012. So roughly, so that integration and test everything and put it all together process took 2 years here at RAL Space. This was a very big milestone for the MIRI team. And you can see that not only did we pack it up, but we gave it a nice label on its box, declaring that it was the first instrument to be delivered. So we started last and we delivered first. And I think we were all really pleased and excited about that. But there was something else really key about this delivery, because as part of the issues around whether or not the mission should be cancelled or replanned, NASA had made a commitment in that replanning that they would start in 2012 the integration of the instruments. And the near-infrared instruments had a few problems. So actually it was a really good thing that we were the first instrument to deliver and that we were able to deliver in 2012. So we were very excited about, being the first instrument in and helping to secure that the mission was back on a solid path in terms of integration and getting the instruments there. And in fact, we were almost a year ahead of the next instrument, and we went through a whole test campaign integrated with one other instrument before the remaining 2 near-infrared instruments joined us. So this picture became, British Airways took a picture of it as well, going on their plane. So this was a massive milestone for the JWST project, not just for us. And this picture developed a life of its own. So people rather liked it. So NASA took it off the box and kept it. And then various team members signed it when they went out to support some of the testing. And by the time we got to the testing at Johnson with the integrated test, with the integrated in with the telescope, it was still pinned up on a wall at Goddard for people to sign it. So there's a few people didn't sign it that were involved in that testing, but it moved from Goddard to Baltimore. And then during the commissioning, the team members that were supporting the commissioning are also signing the picture. So this is, and the plan at the Space Telescope Science Institute is to pin our picture up. And it all just started with, I don't remember who, maybe it was Paul that had the idea of printing the picture out and sticking it on the box, and then somebody else had the idea of signing it. But anyway, it's a nice thing. It's a nice thing, definitely. So, and this is MIRI at Goddard, wrapped in its thermal shield, where it started to meet the other half of MIRI, which is our cryocooler, which you can see in the top of the picture, the little gold round thing, also sitting out on a hexapod to keep it well separated. That's the cold head that provides the cooling of the instrument to 7 Kelvin. So I'm going to sort of jump forward through all of those test campaigns at Goddard and talk now about what happened during commissioning. And this is the JWST primary mirror. It's a picture of all the segments and all the mirrors that go into making up the optical chain of JWST up until the point that you get to the instrument. And you can see that they are all numbered. So the letter is the shape on the mirror. What you're doing is you're taking these hexagons and you're packing them close together, and you want to make essentially a parabola. So the ones in the middle the mirrors have to have a different curvature on them from the ones on the outside edge. So you've got A-type mirrors, B and C mirrors, and then you know exactly which mirror is which on this map. So this is actually the very first image that JWST took after the launch, after it had all deployed and all of that was working. And what you're looking at here is not an image of a star field. You're looking at an image of a single star that was chosen because it was isolated and there could be no confusion about what we're seeing. And you're looking at, because the mirror, although it was perfectly aligned on the ground, this mirror, the hexagons have to be aligned to each other with an accuracy that's smaller than the width of a human hair. So when you stick that on a rocket and you shake it, the right answer is not to try and keep it still. The right answer is to let it move and then say, well, we can tweak it up and phase it up again afterwards in space. So the back of each mirror, it can tip and tilt like this. And you can also slightly stress the back of the mirror to adjust the shape. So the first image looks like this. And the first job was to tilt each mirror and go, all right, now we're tilting A5. Which image of the star is moving? Ah, yes, that's the image that's coming from A5. Once you've done that, you know how much the mirror is wobbled out of place. So you know then how to unwobble them out of place and put them back in place so that you have an image coming from each mirror. And like I said, the supports on the back of the mirror stress it slightly. So you get them all in the right place, so you're reproducing the map of the primary mirror, but they're not making great images. So then you adjust it so that each mirror is making the best image that mirror possibly can. And then when you've done that, you have to then tilt them all so that it becomes a single mirror making a single image rather than lots of separate images from each mirror. So that is what they call phasing the mirror and aligning. And at that point, JWST was perfectly aligned. This process matched so well the modeling that had been done of how it would work and what would be expected, that commissioning got slightly ahead of itself because they managed to skip one final round of going. So the plan had been to go around the loop, then you take some images, and then you go around the loop again and you gradually tweak it up. But the last loop of going around that plan didn't happen during commissioning because it wasn't needed. And at this point, MIRI wasn't cold. And well, now MIRI's cold because there's MIRI data up there. But when they were phasing up the mirror, MIRI still wasn't cold. So then after that, we got cold. And this is how JWST looks at the sky. So this is now the Large Magellanic Clouds. So this is the stars in our nearest neighbor galaxy, looking at them. They are all perfectly in focus. So all the instruments have to be in focus at the same time because they look at neighboring pieces of the sky. And you can immediately see, if you look at the MIRI image, how it differs from the near-infrared images. So if you look at the near-infrared images, you'll see patches where you can see more stars, and they're sort of brighter and redder, and then there's black bits running through them. Those black bits are where the dust in the galaxy is hiding the light from the stars from you. Whereas with MIRI, what you see is bright stripes. And those bright stripes, that's the dust, that's the warm dust glowing in the mid-infrared. So just to give you an idea of how revolutionary MIRI is, this is a bit like Nick showed you. When you have a small telescope, you look at a much bigger area of the sky, but in less detail. So this is the MIRI data on the Large Magellanic Cloud being compared to what we had before JWST was launched. And you can just see, I mean, this just blew my mind actually seeing what a difference all of that resolution, all of the things that I have been talking for 25 years about why it would be important to have a mid-infrared instrument on this telescope, it's there, right? You go from that to that, and the difference in what that tells you and what you can study is just massive. It is a revolutionary change in capability for mid-infrared science. And very nice that it is beautifully and perfectly in focus. So overall, the performance of the observatory is better than it's better than the requirements and the pre-flight exit. It is really excellent. Some of that is what I talked about earlier. The optics alignment went extremely well, and I think that was down to the amount of detailed modeling that had gone into the algorithms and how it would actually be done. So the optics are better aligned. That means the point spread function is sharper, and you get more of the energy from the star in that central star sharp peak. So you can see in more detail than we expected. The observatory is more time stable, and this again is back to the optical quality. So the temperature of the observatory drifts slightly because you've got the sunshade pointing back to the sun, so it's being heated by the sun, and then you're moving a telescope around on this side of it. So you're always seeing slightly different warm patches, and that drift of the temperature is changing the stresses slightly on the back of the mirror. And again, I think this is about the modeling that was done and how much they really got the mirror mounting right. The observatory pointing is more accurate than the requirements. One of the reasons for that is Gaia. So when the requirements were developed, the Gaia catalogs weren't there. Now we're using the Gaia catalogs to help us find our way around the skies. And the mirrors are cleaner. They have been kept through, you know, there was Ariane Space, and ESA really went to a lot of work in the integration because JWST was a naked telescope. There's nothing round the primary mirror, which I think is also relatively new. So there was a lot of concern about the amount of contamination this might get when it was being integrated with the rocket. And I think Ariane Space did a really great job on not just the launch trajectory, but in how well they kept the mission clean. And also how well it works to make sure that you're always keeping your thing that's folded up that way up when the dust kind of falls past it rather than onto it. So that's great. So the bottom line of that is that all the science instruments also have a higher sensitivity than the pre-launch expectations by something on the order of 10%. So overall, we've got a mission now that is 10% better than the requirements, which is absolutely fantastic. And it's got a mission lifetime that's nearly 4 times longer. So it is really, I don't know, when I just looking back and even just writing the slides for this talk and thinking, wow, it really does work. And it's a massive technical challenge and demonstration of technology to have done this. So I've talked before I talk some more about the science, I thought rather than talking about the technology and the challenges and what's being achieved, it would be nice to talk about how it was done. And I would say how it was done is that people made JWST and they made MIRI. So you've seen some of the people who made MIRI in my earlier things, but about 20,000 scientists and engineers and technicians from all over the world contributed to building this mission. And it is people working together in teams, people with the willingness to work across engineering cultures, across language barriers, and just solve the problem. And the other thing that made it happen was not that any one individual person, there's lots of great people in the teams, but it's also about systematically solving things one problem at a time. And that is what the team did. And there was always an issue. This is so new. So, I mean, we all know space missions are complicated anyway. And then you know, the added complexity of something that had to unfold and line up and all the rest. So just systematically going through one problem at a time, solving it, moving on to the next problem, solving it. And that That's how it was done, by people in teams, solving problems. So I'm just going to talk a little bit about some of the new results. There are new results starting to be really developed. New science is happening already. This is a mission that's only been operational for 4 months, and yet you know, the science is really happening, and so there's something new, I think, in all the different areas of science that we wanted to address with a mid-infrared telescope, with a near-infrared telescope in space. A large telescope cryogenically cooled in space is an amazing facility for addressing everything from how do galaxies form and evolve to how do planets form around stars, and what are planetary systems around other stars really like. So this is, as I said earlier, this is just kind of a view of some of the things that I'm most excited about that have been coming out in the early science, because I can't possibly show you all the data and all the images. So one is, in fact, and of course this goes right to the original science cases for JWST, is about the insights it's giving us already into the early universe. You have probably seen the image before, because it was the first press release image that NASA put out. This field and image is now being mined by scientists all around the world for what it tells us about the early universe. And the answer is, the early universe is not quite the same as what our models were saying it might be like. That's what observational astronomy is there for, to go and look at things and find things out. So we're seeing red galaxies that are not seen by Hubble. So the graph at the top, the gray area, is the numbers and the galaxies found by Hubble in that field as a function of redshift. And the black line is ones that have been found in the JWST data, and you can see that the two overlap. So JWST is finding the near-infrared images with JWST are finding things that didn't show up in the Hubble images because Hubble just didn't detect them. There are far more disk galaxies. So if you look at the plot at the bottom, the Hubble, there's the data with the rings is JWST, the data with just the error bars is Hubble. There are far more disk galaxies at intermediate redshift, so sort of halfway through the evolution of galaxies since the Big Bang. So that means the galaxies are more fully formed. Disk galaxies are fully formed galaxies than we expected. So they're not these kind of, did galaxies first form as some blobs merged together? These are fully formed disk galaxies, a long way away. We've also been surprisingly easy to find some very high redshift galaxies. And so they appear to be more massive, and some of them have some very extreme luminosities. They're very, very bright compared to what was expected from the modeling. There's only a handful of these galaxies, so exactly what that means, I don't think anybody knows at the moment, but it's certainly it's exciting. If you want to know what a probable redshift 16 galaxy looks like, it's the little image at the top. It's a very clear detection. But of course, what we really need now is the follow-on spectroscopy to make sure that we're interpreting these correctly. But there's some really exciting science coming out of just the very first images. And I should add that this was a few tens of hours. Between now and February, there's more than 100 hours of time scheduled on the Hubble Deep Field. So this science is really going to open up in the next few months in a new way. I mean, we can see the hints already coming, the kind of predictions in the models of what we would see are not quite right. This is Stephan's quintet. I put this in just because it's one of my favorites, and I've always been interested in interacting galaxies. And on the left, you see the Hubble image, and the new JWST image is the MIRI image of Stephan's quintet. And again, is showing you, I still think this is my favorite of all the images. is showing you the difference of what MIRI tells you. So if we look at, so the Stephan's quintet is actually 4 galaxies that are interacting and ripping each other apart. And those are the 4 galaxies that are on the right of the image. And then the galaxy that's very blue in the MIRI image, and it looks like a beautiful spiral in the optical Hubble image, that galaxy has got nothing to do with the other 4. It's a completely different distance from us. So it's just a plain spiral galaxy. But when you look at the MIRI image, the bright blue galaxy, it looks like lace. You don't really see the spiral arms, because what you're seeing is the feedback of the dust and the interaction of the dust that's happening between the spiral arms. And there's image after image after image now, several of them being released by NASA, where you see this massive difference between, if you look at a relatively nearby spiral galaxy in the optical, and if you look at it with MIRI, and this feedback between the spiral arms, the models of the spiral arms and how star formation happens and how shocks works, it had to be happening, but now we can actually see it and study it in some detail. And the other thing I like about this is the galaxy at the top is what's known as a Seyfert galaxy. So it's a Seyfert galaxy, means it has an active black hole in its center, and it's very, very bright, but it's also very, very dusty. And this galaxy was first found by the first infrared, found to be potentially an active galaxy by the first ever infrared survey of the sky, IRAS. It's one of the sources that turned up as what they called unusually bright. Okay, so it was looking like it was much brighter in the infrared than it should be from optical images. And subsequently, the X-ray astronomers found X-ray evidence that there is indeed an active galactic nucleus in here. But what is really nice is in the MIRI image, you can see the diffraction spikes. There's a great big bright point source coming, booming through out of that galaxy. And that is interesting that we've detected it so well. There's a big bright point source that is also further evidence for a black hole. But what we've actually been able to do now is spectroscopy of that source. And there are some interesting things in the spectroscopy. So this is now understanding how individual galaxies evolve and what's happening in the nuclei of individual galaxies. The first one is the spectrum at the top, where you can see there's a little purple marker on the spectrum and it says argon. That argon line, to see that argon line in the mid-infrared, you need to raise the gas to a temperature that is much higher than you can do with stars. So again, this is evidence that the gas in this galaxy is not just being heated by stars, is actually being heated by the energy that is being generated by a black hole gobbling up matter in the center of the galaxy. And that's now, so this fits very well with what the X-ray astronomers have said about this galaxy, but it is really good in observational astronomy to have more than one way of studying these phenomena. The other thing that is interesting, and that's really interesting to me, is that although we can now narrow in on the very, very bright source in the center of this galaxy, that source is still heavily extinguished by dust. And the dust is so dense that it is protecting the survival of molecular hydrogen. Hydrogen molecules are really easy to break up. They should not survive anywhere near the radiation field that's coming off of either a hot star or, even worse, an active black hole. So the fact that there are hydrogen molecules in that spectrum at the bottom is telling us something about the density of the dust that is surrounding this. And it's so dense that, so more exciting. So this now is showing the power of JWST to study galaxies in our nearby universe and understand more of them. So I'm just going to kind of skip somewhere else now. And it's around the ability of JWST to study exoplanets. So the way that we find many of these exoplanets is what and the way that we want to study them is with what we call transit spectroscopy. So first of all, a transit means that as the planet's going round its star, the planet blocks out some of the light from the star. So if you monitor the light from the star, the light drops out, it fades because the planet's in the way. And then when the planet moves back out the way, it comes back. This is how many exoplanets are found. But what we actually want to do is do that with a spectrograph, which is technically much harder. And actually it relies on the telescope having extremely stable pointing, because otherwise all you see is systematic effects, because your spectrograph is drifting around. And this is the first, so the water in this exoplanet atmosphere was already suspected from previous data. So this isn't an exciting new result. What's exciting about this is the accuracy with which the water spectrum is identified. And there is a lot more like this to come from the exoplanets. And the other thing that's interesting that you can do with exoplanets goes back to my coronagraphs, where you can take images of planets that previously you only inferred were there because they blocked out the light from a star occasionally. If you can take images, you can measure sizes, you can get better estimates of masses, you can get better estimates of the actual distance from the star. So now you're starting to really constrain, just by taking a picture, what you understand about planets and indeed planetary systems. Watch this space in around other stars. The graph is just a plot of how accurately we can do this with lots of known exoplanets named on it that are part of the JWST set of targets that will be observed this year. So again, this is the first result, tempting us with what's to come in the future. And I talked about looking at dust. So this is now one of the things we did with MIRI was we put in filters that were chosen so that we could image by looking at worm dust rather than try and look through it. So this is a binary system. One of the stars is a Wolf-Rayet star. It's a star that's dying, and it's dying in a rather pathetic fashion. It's dying by every so often it can't quite get up the energy to keep burning stuff, and it spits a bit out. So every so often it's throwing out some of its stellar material, but because it's in a binary, there's another star going around. So what's happening is the Wolf-Rayet star is going poof, and then the smaller star is coming around and compressing that gas. And by compressing the gas, you're making dust, tiny little dust grains of polycyclic aromatic hydrocarbons. So it was suspected from previous data that this system might have formed a dust ring around it at some point. What we have actually found is 17 dust rings corresponding to one every 8 years and covering something like 100 trillion kilometers and 100. So this star for 130 years has been spitting out material that it's neighboring to the dynamics of the system of them being compressing and making into dust. And that's what creates the beautiful sequence image that you've seen. So it's a kind of a unique opportunity now to really look closely at dust formation processes and the chemistry of dust formation. And this is Jupiter. So this is a combined image of both, and a lot of the science is coming from adding MIRI to the near infrared. It's not things that the mid infrared does on its own. It's about having that complete picture across the band. So this is Jupiter. The thing that fascinates me about Jupiter is, so the side on the left of that image is in daylight just because of the timing, and the side on the right with the red spot highlighted is in the dark. And what you can actually see if you look closely at it, you can see the ionosphere of the planet. So you can see the limb of the planet, and then there's a tiny little black ring, and then there's more light. That's the ionosphere of Jupiter. And one of the things that the early release science team are really now looking at is using the spectroscopy of the spot to study the energetics of how these storms are actually driving the physics in the ionosphere in a planet that's not ours. So I just think, I'm not a planetary expert by any means, and I just think that the Jupiter science is utterly amazing that you can do that, study the ionosphere of another planet. Maybe somebody who's a planetary expert is going to tell me, no, I've been doing that all along. But anyway, I think it's fascinating. Go on. There we go. Okay. So this is an unusual pair of JWST images. Right? The one that is very blue with the red fingery shape moving out on it, that's the NIRCam image, and the one next to it is the MIRI image. And you can see two things. One is the NIRCam image is full of stars, but there are no galaxies in that image. And that is very unusual. One of the features of JWST data is that there are annoying little galaxies everywhere in it. But the reason there is no galaxies here is that this is in a region in the Eagle Nebula, so it is pointing into our galaxy where the dust and the gas is incredibly dense and new stars are being formed. So in the NIRCam image, all of those blue stars, those are hot, young, newly formed stars. They were formed in the dust and they burned holes. And if you look at it, it's got a bubbly structure. They burn away holes as they come out of that dust. So you're not looking, and you can't, and even then, it's still got so much dust and dense gas in there that you can't see through it to see that there's any other galaxies. The MIRI image is where we have used our filters that we put in that were designed for looking at the dust rather than trying to look through it. So the MIRI image is showing you where the really dense dust is, and those few little stars that you can see peeking out from it, those are really newly formed stars. So there's actually, and this goes to what I was saying about needing to understand the relationship between the star formation and the dust and the region the star is forming in order to understand how planets form around stars and to constrain that. And one of the early release science programs is called the Ice Age, and it's about trying to study the ices and the dust. So again, quite a strong UK involvement in this from Helen Fraser's group at the OU. Where I've marked the purple star, what they have done is they found two tiny bright stars that are just on the edge of that incredibly dense dust that you can see in the MIRI image. And what they want to study is the chemistry of the ices and the ice mantles that are on the dust grains there. So they've done spectroscopy. There we go. So this is two stars. You can see how very similar the two spectra are. All of the different features are identified. So the really strong feature that you can see, that's the ice band. That's not new. What's new in this is all the little weak features and the match of having the strength of the big deep band like this. So you can see that's a water band, and then there are some weaker water bands, methane, silicates. So this is a really rich. So a simple question. We've looked at this has only ever been done, I think, along about 2 other lines of sight in the galaxy where there was a lot less dust. So here's a simple question. When you look at a region that's really so full of dust you can hardly see in it, is the dust the same as the dust when you look somewhere else in the galaxy or not? Would it be chemically different? It probably might be. It's being heated differently. It's being treated differently. But that's it sounds like a simple question, but actually we don't know the answer for dust. And one of the reasons we don't know the answer is because we haven't been able to look at the dust in our galaxy in lots of different directions and lots of different places, so you can start to try and understand the chemistry that's in the dust rather than the chemistry that's in the stars and the stellar motions. So this is really demonstrating the power of JWST to be able to study the dust and the ices in these dense regions in our own galaxy in unprecedented detail. So this, I think, the extinction, the amount of dust in the line of sight to here is about 2 orders of magnitude more than any of the lines of sights that have actually been done before. So being able to say that actually the dust does look the same, that's an interesting result. And I think it's fascinating, but I also think this will be an area where we'll see a lot more science to come. So, like I said, I think this is only the beginning. There are more than 100 published papers just from that first data that came out in July. We are detecting the faint galaxies more easily than we thought, partly because the sensitivity is better, but partly also because I think the universe is a bit different from what we thought it was. We've done spectroscopy of stars that are forming and dying, images and spectra of exoplanets, and even solar systems, and elucidating sort of complicated physics and chemistry and other solar system bodies. So this is really just the beginning of a new era of scientific discovery that JWST is enabling, and is that classic thing of when you look at the universe in a different way and in more detail, you find things that you didn't expect, you didn't know. How can you know if you haven't looked? So there was some talks earlier about how much space inspires. I think JWST is inspiring as a technology, as well as the science and the beautiful pictures. So one of the things we have done, and it was the MIRI team really supported and had support from STFC and the Space Agency to do this, was we tried to build a really strong, in the UK, public engagement activity, not around this is a NASA mission, but around this is a NASA mission and British technicians and engineers contributed to it, telling the engineering story. And the way we did it was by partnering with other organizations that are experts in how you communicate in different forums. So planetaria, science centers, but also experts in developing material for primary schools, with the IET for materials for secondary schools. And that means that, of course, this had a much bigger reach than if we had just tried to do it on our own. But the team has been very, very active in making their time available to these organizations to support them in developing the things that are local to us in the UK about JWST, and creating educational material from it. The work was actually led by Olivia Johnson of STFC's National Labs PE team. Before the launch, we estimated that we had reached 500,000 people. And I don't just mean because we told them a story about something, I mean 500,000 people who engaged in an activity, what the public engagement people call, you know, quality engagement. We've also, and I hope we will go back when JWST has done some more science, had an exhibition at the Royal Society. So really trying to push the message around the UK as a part of this, not just the fantastic science, but we helped build it. And I really care passionately that people understand that it's not just NASA that does this, that space is for everybody, and the sky is for everybody. Anybody can walk out and look at the sky and look at the stars. So, you know, the universe is beautiful because it's beautiful. So the images are beautiful and the science is amazing. And I think, you know, a really big thank you to an awful lot of people, and especially the long-term support that came from the national funding agencies, the UK Space Agency, STFC and their partners across Europe, without which there wouldn't be a MIRI instrument. There's a whole pile of people actually that helped me put the slides together by generously sharing other material, and lots of people that helped along the way. I know there are people sitting in this room that sat on peer review committees at the time when JWST was being proposed and agreed it was a good idea that the UK should invest in MIRI. So thank you to absolutely everybody. And I just want to leave you with one final thought, which is this. The best camera might be one at L2, but I think the best camera is the one at L2 that has a mid-infrared camera and spectrometer as part of it. Thank you very much for listening.
Thank you, Gillian, for a truly inspirational talk. And what I love so much is that although you've ended with the amazing science that's happened so far, what's even more amazing is the journey that you were on right from the start and taking through the engineering challenges and the challenges of leading such an amazing team. And you really brought it home and made it personal. So thank you for that. I'm sure there are some questions in the audience.
Gillian, thanks so much for that. I don't think I'm ever going to get tired of listening to what we're getting out of James Webb, or looking at the images, or hearing about the data. And we know that it's going to keep researchers busy for years to come, many, many years, more than we perhaps thought. So that's absolutely wonderful. And you might kill me for asking this question, but you said JWST was 25 years in the making, maybe a little bit longer when it was just a twinkle in your eye and other people's eyes. So I have to ask, what do you want to see next? What comes next? What comes after JWST?
Oh, we could use another one, please. Actually, I think, you know, a future ultraviolet mission will be very important, because we're sort of, you know, and it is about how astronomy at different wavelengths all ties together. So I think ultraviolet missions and X-ray missions to complement this are going to be very important. And I also think that what Nick mentioned about a near-infrared Gaia is incredibly important, because being able, so we can do quite a bit of kind of looking at some of what's happening in our galaxy, but looking towards the center of our galaxy, but being able to fill in that piece of kind of, I don't know what you call it, archaeology, how all the bits fit together in an individual galaxy is a really important question to answer. And I think, you know, so that future that would maybe bring together some of the things we're demonstrating in the near infrared with JWST, with the kind of capabilities that Gaia has, be really important. And of course, exoplanet missions.
We've got a question online.
Want them all.
In the same line, actually, what will the JWST replacement look like in, say, 30 years' time? Would it be?
Well, it's not a replacement, it's successors. Yeah. And so you learn a lot of science, and then that helps you to ask the question a different way. And then you want to answer that new question.
Great. And another question, given how many years there were between finishing MIRI and launch, are there any changes you would make if you were to design MIRI today?
Ooh, that's a good one. Well, you can always do things. I mean, you learn by doing, don't you? So you can always do things better or differently. And, you know, I might like to have 6 detectors instead of only 3, and then I could do a lot more. But yeah, I think it's all right, actually.
One final question, Richard.
Gillian, brilliant, excellent. I mean, really stunning stuff there. One of the most striking images, of course, for an astronomer is the deep field image, which is absolutely stuffed with galaxies.
Yes.
I don't think you said it, and forgive me if you did, but can you comment on the most distant galaxy you see in that image?
The most distant galaxy is probably at a redshift of 16. So it's 30 billion light years away. But that needs spectroscopic confirmation. So the colors of the galaxy would indicate that that's how distant it is. But until we get spectroscopy, we can't be sure.
Okay, Thank you very much. I'm afraid I won't be able to take any more questions because we have overrun. I did let Gillian just talk about the amazing science.
Yes, sorry.
No, because I think everybody here would want to hear what you have to say. It's traditional for us here to give a small gift to our keynote speaker as a token of our appreciation. The work that you do is truly inspirational, Gillian, and I'm very, very grateful that you chose to speak here today. So thank you very much. And we'd like to present you with this image here. It's a Sentinel-2 image of an area that you might recognise. You might recognise Edinburgh there. So
I might squint at it and see if I can find my house.
I think you might well. So thank you very much indeed. Thank you.
The detail, that's amazing.
I think you could spend quite a long time looking at that image.
Yeah, you could, indeed.
Thank you very much. If I can just say a few final words to close the 18th Appleton Space Conference. I'd like to thank you all for attending today. It's been great to be back face to face, and there's been an amazing array of talks, finished off amazingly by Gillian's talk on JWST. It'll be great to have you back in a few years' time, Gillian, to talk some more about this amazing science that's to come.
I'm not coming back. You can have one of the STFC Web Fellows come and tell you about the science.
I will do that too. Thank you. I'd just like to say a few thank you to you all for attending today.